Hi everyone, my name is Siki. Today we are going to look at a few tutorial questions related to the capacitor.
So today we'll continue this example 26. Okay, example 26. Okay, so you have spherical capacitors. Okay, so spherical capacitors, so meaning that it is a sphere. So it is a sphere. Okay, it is a sphere. Okay, so the inner radius is 1.5 and the outer radius is 4 centimeter. Okay, so it has inhomogeneous dielectrics. So inhomogeneous dielectric, okay, is means that the dielectric value of the material in between this inner conductor and also the outer conductor will change. Okay, it's not homogeneous. Okay, so previously I explained to you before what is the meaning of homogeneous. Homogeneous, it means that the dielectric constant of the material is consistent at all positions, okay, of the material or of the dielectric. Okay, so is inhomogeneous means that it will change. Okay, you can look at this formula. Okay, so this one shows the dielectric. Okay, so this shows the dielectric property value for this inhomogeneous material, and it is represented by 10 times epsilon naught divide r. So when the r change, the epsilon value will change as well. So we call this one as inhomogeneous dielectric. Okay, so you have to calculate the capacitance per meter of the capacitor. Okay, so we first of all we draw the shape. We draw the shape. Okay, so this one is the inner conductor, and then we have the outer conductor. Okay, outer conductor, right? So if the inner conductor is positively charged, okay, then the outer conductor will be negatively charged. Okay, so these two conductors, they are in the shape of sphere because it's a spherical capacitors. Okay, so the electric field will be in these directions, right? It will be in these directions. Okay, in these directions. Okay, electric field will be in these directions. And radius, A will represent the radius for the inner, okay, and B represent the radius of the outer sphere. Okay, calculate the capacitance. So we refer back to our formula that we derived in the class, okay, which is this one. Okay, so for the capacitance of the spherical capacitors is equal to this. Okay, 4 pi epsilon. Okay, so I will just write down here. Okay, so this is the formula that we derived previously. So if you are going to take this one, okay, and replace it here, so what will happen? So when you replace this thing inside, okay, so your formula, when you replace the value of A and B into the equations, so the capacitance of this spherical capacitor still cannot be calculated because there will be a variable R. There will be a variable R, right? 4 pi 10 epsilon naught divide R when you replace it. 1 over A minus 1 over B. Okay, you replace the value this one, you calculate using the calculator, all these things, but still you have this value which is unknown. So meaning that you cannot calculate the capacitance per meter of this capacitor. Okay, so for this inhomogeneous dielectric, okay, inhomogeneous dielectric, you have to remember you have to rederive the equations. Why I have to rederive? So you can look at the calculations over here. Okay, so we always begin with the Gauss law, right? So Gauss law, everything. Okay, so when you proceed with the Gauss law, okay, you can get this thing. Yes, it's correct, you can get this thing. Okay, then you can get the formula for the E. But when you replace your E into the V over here, okay, you are going to integrate the length, right? The dr. Okay, so here, the epsilon here, it is a function of r and it should be considered when you perform the integrations. Okay, when you perform the integration, you should consider the R inside this epsilon. Okay, so that's why we have to rederive again. Okay, so I won't start all over again. Okay, but I will just start from this V. Okay, I will just start from this V, calculate the V. Okay, so might be here, I will just write down. Okay, so derive, okay, derive the E, okay, based on Gauss law, okay, Gauss law. So you will get this, your E equals to, right, so Q over 4 pi epsilon R squared. Huh? Q over 4 pi epsilon R squared and R. Okay, so this one is the R, right? You get it from the Gauss law. You can refer to your notes. We talk about this Sunday. Okay, refer to the PowerPoint, refer to the module, you get this thing. Okay, so we go to the V over here. V over here. So this one will be the integrations, okay, of this E. So for this epsilon, I will replace it with the epsilon given by the question, which is 10 epsilon naught divided with the R. And you have the R square, right? And you're going to integrate with respect to the R. Okay, so this R is the path of the electric field, okay, in the spherical capacitor. So it is in the R directions, R directions. Okay, so this one will be R as well. Okay, so from the inner radius to the outer radius, inner radius to the outer radius. So you can see there will be some changes, okay, on the formula. Okay, because this thing is going to be cancelled with this, so you left the R, right? So it will be, you take out the constant, okay, so this one will be 10, so you can multiply directly 40 pi epsilon, okay, 40 pi epsilon naught, okay, so you integrate A, B, so this has become 1 over R dr, right? Okay, so this thing is cancel, you cancel it to be 1. Okay, so you should get this 40 pi epsilon naught, 40 pi epsilon naught. And then this one will give you the long R, right? Long R, B and A. Okay, B and A. So this one will be equals to Q over 40 pi epsilon naught. Okay, long B over A. Long B minus long A equals to long B divide A. Okay, so if you compare this one with the previous one we have, you see it's different. It's different. Okay, there's no long, because it is R squared, and in this case it is R. Okay, so the formula for our capacitance will be Q over V. Q over V. So you can calculate now what is the formula of your C, okay, over ln B over A, and also the Q. Also the Q. Also the Q. So you can cancel this thing. Okay, cancel this thing. So your C will be equals to 40 pi epsilon naught divide ln B over A. Ln B over A.
Dekat situ kan dia ada negatif kan. Kalau kita tak letak negatif.
Oh, okay, negative, Yeah, right. So for this negative, you can still put this thing here, put this thing here. Okay, put this thing here and put it here. Okay, but at the end, you will modulus it. You will modulus it. You won't consider the negative for the calculation of capacitance. You won't consider the negative. You won't consider the negative. Okay, if you want to take into consider, let me show you what if you take into consideration the negative over here. Okay, maybe if you, in this case, I will write in different colors. If you want to consider the negative, so maybe if you consider this one inside, right? Okay, if you consider this one inside, Okay, so you will get another formula, right? Q equals to 40 pi epsilon naught ln A my over B, right? Because it will be negative ln R. Okay, negative ln R. If you want to take into consideration the negative, then it will be like this. Okay, because for this one, this is ln B minus ln A. Okay, if you add this negative inside, then it will become ln A minus ln B, right? So you will get this thing, the red one. Let's see what happened. Okay, so of course lah, the C will be different. And the C will be different. The C will be 40 pi epsilon naught. Okay, ln A over B, right? A over B, right? If you consider the negative, So let's see what's the answer for this when you replace the value. So what's the value of the A is 1.5, B is 4. 1.5 and 4. Okay, so you calculate. 40 pi epsilon naught ln 1.5 and 4 centimeter. 4 centimeter, correct? 1.5 centimeter. Okay, so please calculate the answer for this. And for this one, okay, it will be 40 pi epsilon naught, okay, and ln 4c over 1.5 c. C is centimeter, you can cancel it, So tell me what's the answer for this. Can you tell me? So for this one, you will get 1.13 nanofarad. Okay, so 1.13. This is nano negative 9. Negative 9. Okay, how about this? What you will get? You will get negative 1.13, right? Is it? Are you getting negative 1.13?
Yes.
Huh? 1.5. You get negative, right? Negative 1.13. So when we are telling people what is your capacitance of these capacitors, we will never mention the negative, right? So capacitance is always a positive value. Okay, so the capacitance, okay, we only take the positive value, even though you calculate this one as negative, blah blah so on. Okay, you can put it as 1.13 nanofarad. This is the capacitance. Okay, you never represent it in negative. It is just like I'm asking you, what is the length of this pen? You're not going to tell me that the length of this pen is negative 8 centimeter, for example, right? You will never say the negative. Okay, you will say that this is 8 centimeter because you're just concerned about the magnitude. Same as this case, for the capacitance. So don't worry if you have a negative. Okay, what happens if your equation of the C you have negative? You can just ignore it. Okay, because after you replace the values, okay, you will just take the magnitude only. I will just take the magnitude only. Alright, clear?
Yeah, doctor.
Okay. Any questions? Just ask me any question during tutorial session. Okay. So if no questions, we'll move on to this one. Okay, exercise 27. Okay, thank you for the response. Okay. So now you have a cylindrical capacitor. Okay, so it has inner radius and outer radius. Cylinder capacitor. Okay, so the space between the plates is filled with inhomogeneous dielectric again. Okay, so the R is centimeter. Okay, you see centimeter, A centimeter, B centimeter. So find the capacitance per meter of the capacitor. Okay, so first of all, maybe we draw first the capacitance. So you have this, okay, inner, and you have this outer, right? Okay, So you have inner, outer again. Okay, you have outer again. Oops, slightly bigger a bit. Okay, then you join them together. And join them together. So this is your cylinder, right? Cylinder, right? Cylinder. Okay, so you have the inner plate. Inner plate. Might be the inner plate is positively charged, and the outer plate is negatively charged. Huh? It doesn't matter. It can be the other way around. Inner negative, outer positive. Okay, it's fine. Okay, so if this is the charge conditions, when you draw it in 2D, meaning that you view this cylinder, okay, from this side, you will see the circle shape, right? Two circles shape, circular shape. So one circular shape, okay, and you have the other circular shape, okay, circular shape. Yes. Right. So inner will be positive, okay, outer will be negative, okay. So the electric field directions is outward, okay, in the R directions. R directions. So the R direction here in this case it is uh, this R directions. Your electric field in the R directions. Okay, so look at the capacitance equation that we derived previously. Okay, you can look at it. Okay, it's this one, right? We have coaxial capacitor. Coaxial capacitor is in cylindrical shape, so it is the same as the cylindrical capacitors. Okay, so you have this 2 pi epsilon L long B over A. 2 pi epsilon L, 2 pi epsilon L, okay, is a long B over A. Long B over A. Okay, so you know what's the definition, right? So this one is the dielectric of the material in between this inner and outer, okay, which is this one, the material. Okay, the dielectric property, the permittivity of the material in between steps. Okay, so question says that in this case, oops, okay, my epsilon is equals to 10 plus R over R. Same like the previous case. If you replace this one into here, okay, okay, you can replace the value of B, you can replace the value A, you can also replace the value L. But how about the R? Oh, you cannot replace anything, right? Cannot replace anything. Okay, this doesn't mean that this C will change its capacitance, okay, along the radius. Okay, the capacitance should be a value. Should be a value. So for this case, same like the previous questions, we cannot use this thing directly, or cannot use directly. We have to rederive again. Okay, so we have to rederive. Okay, so let's see where we should start. Okay, you see this thing? So this one is the Q that we get by applying the Gauss law, right? So from here, we get the E, yeah? We get the E. So this one is showing the directions of the electric field because you see this case, the positive is at the outer conductor, okay? For the inner one, it is electron. So the direction of the electric field is in inward, okay? Negative R directions, negative R directions. So in this case, for our case, I will just take this thing, okay? Take this thing, so derive again, you get your E equals to Q over 2 pi epsilon R L, right? R L, yeah, R L. And in the R directions, I write in the R direction because in my diagram, you see my electric field is in the R directions. If I want to say that it is in the negative R direction, then it will be like this. Okay, but this is not the case because inner is positive, outer is negative. You should follow the you should follow this the according to the locations of a positive charge and negative charge. Okay, so again, I go to this one. So I will have a negative here, right? Okay, so I guess you already know what you have to do, right? And this is R directions. My DL will be the length, okay, that this electric field go through. Okay, so this electric field go through in these directions. Okay, so the length is depends on the value of R. So it will be dr. And dr in the R directions. Okay, you don't confuse this one and this one and think you can cancel it. No, this is a unit vector. Okay, this is unit vector. Okay, now interval for the R, it depends on the radius of the cylinder, right? So you have A and B. A and B. Okay, so you will have this 2 pi epsilon. Oh yeah, epsilon, it is, what is the epsilon? Okay, this is epsilon r, not epsilon. Epsilon r, epsilon r. I hope you know the difference. What is the epsilon and epsilon r? So this is the relationship. Okay, so I will take this epsilon naught here, and the L is here. Okay, then I integrate A and B. So in this case, I put the value of epsilon r, which is 10 plus r over r, multiply with the r. Okay, so this thing is the epsilon r. Okay, epsilon r multiply epsilon naught, you will have the epsilon. Okay, you will have the epsilon. Okay, so you can cancel it. You can cancel it. So you have this q over 2 pi epsilon naught L. Okay, integrate A B 1 over 10 plus R. The R. Okay. So now you have to continue with the integrations. Okay. Okay, so this one will give you ln 10 plus R. Okay, ln 10 plus R and B and A. So in the exam, if you don't know what is the answer for this one, right? Okay, use software. Okay, use software to find out yourself. Okay, or you have any other formulation sheet that shows that how to perform the integration for this kind of equations, then you can use that. Okay, so this one will be net minus 2 pi epsilon naught L. So it's going to be ln 10 plus B, right? Minus ln 10 plus A. Okay, this is minus. Okay, if you don't wish to see negative here, okay, you can multiply it, then this one become negative, this one become positive, then this one will go. So it's up to you. So the things will become this 2 pi epsilon naught L. Okay, if this is negative and this is positive, it's going to be 10 plus A over 10 plus B. Same thing. So this one will be my V, my V. So finally, we can calculate our C. So you have this 2 pi epsilon naught L, okay, over Q ln 10 plus A over 10 plus B. So you can cancel it. And in the end, 2 pi epsilon naught L over ln 10 plus A 10 plus B. Okay, so this one is a C. C. Okay, so we can replace the value. Okay, we can replace the value. A is 1 centimeter, B is 2.5 centimeter. Okay, L is not given. Okay, later I will talk about the L. So this one it will be 10 plus 1 centimeter. 10 plus 2.5 centimeter. You must put the centimeter. Then you must put the centimeter. Okay, so this one is C. So question is talking about the capacitance. If you look at it, capacitance per meter. Meaning that capacitance is F per meter over meter. Over the length. Okay, over the length. So for this C, capacitance per length, okay, this one will become ln 10 plus 1C over 10 plus 2.5C. Okay, so you can calculate this one. 2 pi Okay, so you will have this negative 3.72. This is per meter. Okay, so you can ignore the negative and write the answer. Might be you want to put 37.2 picofarad per meter is also fine. Okay. Any questions? Is my calculation correct? Right, we move to the exercise in module. Okay, so you can refer to your module. So for the question with solution, I'm not going to talk about this. You can look at it yourself. Okay, let's look at the practice exercise 1.19. 1.19. So this is a parallel plate capacitor. Parallel plate capacitors. So you see the dimension is given. Okay, dimension has been given. The separations. Okay, so the dielectric constant of the material in between two plates also has been given. Okay. So let's see what is the equations to calculate the capacitance of parallel plate capacitor. Okay. So this one will be the equations. Right. So it's simple. So the capacitance depends on of course, the material in between, the area, and also the plate separations. Okay, plate separations. So the distance, you see 2 centimeter, right? So for the area, Okay, for the whole plate, you can calculate. Okay, whole plate it will be 5 multiply the length over here, 4, right? Okay, but for this one, for this configuration, you have two material. Okay, so meaning that you have to decide either this one is a series capacitance or parallel capacitance. Series of parallel. Series or parallel. You have to decide it. So how to decide? You look at the plate. Okay, for example, if this is positively charged and this is negatively charged, so the electric field will be in this direction, right? Okay, so the electric field, it has choice, either they want to pass through, okay, the first material or the second material. They have choice. So for these configurations, when you have a choice, it means that it belongs to parallel configurations. Okay, just imagine you have a branch over here. Okay, so there are two capacitor. Okay, so the current, it can choose which one to pass to. Okay, so this is parallel. So for the parallel capacitance, okay, the total capacitance will be the summation of the capacitance of the first capacitor and the second capacitor. Okay, second. So let's calculate what is the C1. Okay, C1, of course, you are going to use epsilon 1, x1, and d1. Okay, so epsilon 1, okay, is equals to 2, right? So you have 2 epsilon naught. Okay, x1 will be the area. Okay, will be the area of this part only. So the area will be 5 multiplied with 1. The area of the plate. 5 multiplied with 1. 5 multiplied with 1. Centimeter, I include it. And the separation is, okay, is 2 centimeter. Okay, 2 centimeter. So you can easily calculate this thing. Okay, so you have this 0.44, okay, picofarad. Pico is times 10 power negative 12. Okay, you get this C1. So for the C2, C2 you use epsilon 2, S2, and D2. D2. So epsilon 2 is 4 epsilon naught, right? Is 4. Okay, and the area, okay, area of the material 2 over here. So this one will be 5 multiplied with the 3. Okay, the area for this part only 5 and 3. Okay, so 5 centimeter, 3 centimeter. Okay, then the separation still the same. Separation is still the same. So you can calculate it. So if you want to cancel, also can 2, right? And the C you want cancel, so okay. So much more simplified when you press the calculator. So 2 epsilon naught. Okay, so you got this 2.65. 66, 2.66 pico. Okay, what's the answer? Okay, right, should be okay. So the C total will be equals to 0.44 plus 2.66, okay, picofarad. Okay, right. So you have 3.1. 3.1. Cool. All right. Okay. Any questions?
Naruto.
Okay, good. Right, we proceed to the next one. Also, for this question, we are not going to try it because I tried it yesterday and we found that there is actually lack of one information, which is the dimension of the sea. Yeah? Dimension of the sea is not reported. Okay, for this one, see C is not reported, so not going to try this one. Okay, we go to this one. Question three. Question three. So question three is using this figure. Okay, so let's see those. Let's see these two uh, figures. Okay, so you have cross sections of two spherical capacitors. Okay, so this is the cross sections. Okay, of a sphere. Okay, of spheres. Okay, because spherical capacitors. Okay, and the separation distance A, B, C has been given. A, B, C. Okay, all has been given. Okay, and the dielectric constant of material 1 and also material 2, okay, they also give you. So you have to find the capacitance of this capacitor. Okay, clear? So we go to the first one, which is this one, A. So this is spherical capacitance. So we can refer to the equations, okay, which is this one, 4 pi epsilon, okay, 4 pi epsilon. Okay, C equals to 4 pi epsilon L, no, not L, okay, sorry, not L, over 1 over A minus 1 over B. Yeah? This is what we have. Right? So this one is a spherical capacitance. So what do you think? Do you think we can use this formula for these questions A? One, you can use. You actually can use this. You actually can use this formula. Okay, now let's look at, yeah, here there is actually two materials, so two capacitors. Why I say I can use? Because basically you this one you derive based on the shape of a complete sphere, right? Complete sphere. So even though, okay, there are two material, okay, in between this inner and outer, okay, but the shape of the spherical shell, the spherical capacitor is still the same. It is still a sphere, complete sphere. Okay, and the dielectric properties, okay, the dielectric, you see, for this one is a constant value, nothing to do with the R or whatever. Okay, so for this case, you can use this formula directly. Okay, but when you decide that you cannot use this one, right? So you should ask yourself, what is the things that change, okay, that make use that make you cannot use this formula. Now you have to ask yourself, okay, if it seems that there is nothing to be changed, it means that you can use this formula. Okay, so for example, we talk about this epsilon r2. If I draw it, so this one will be epsilon r2, epsilon r2. So you have a over here, right? And the c is over here. So might be the formula, the value over here, you have to change. It is not AB. Okay, this is AC, for the epsilon r2. But for the outer one, right? So for the outer one, okay, so maybe it is like this, right? Outer one. So you are dealing with the C and also the B radius, right? So this one will be 1 over C minus 1 over B. So the value will be different, but the formula still the same formula that you are using. Okay, clear? Clear?
Yes, yes, sir.
Okay, so now let's, because since we can use it, right, two material, so we know we have to decide whether it is parallel or it is series. So what do you think? Okay, so I'm showing you the directions of the electric field. So can you tell me what kind of configurations for this capacitor? Who says that it is series? Can you raise your hand if you say that it is series? No one. Any more? Series or parallel? Is this series or parallel? Look at the electric field. Look at the electric field. The electric field must pass through both material. Must pass through both material to reach this side. So this is series or parallel? Who say it is series? So the answer is this is series configurations. Okay, so you always think about current. So for the normal circuit, you can easily determine this is parallel or series, right? So for this one, this is parallel. You know it clearly, and this is series. Series. So parallel, it means that when the current come, it has choice either to go through this C1 or go through this C2. It has choice. Okay, but for this series configuration, the I, it doesn't has choice. Okay, it must pass through both C1 and C2. Both. Eh? So let's look at this one. Okay, here we don't have I. Okay, but we have E. Okay, so you have two conductor. Okay, so this is your inner conductor and this is your outer conductor. So one will be positive charge, the other must be negative charge, positive negative. For capacitor there is no positive positive. Capacitors, both, either one will be positive, the other one will be negative. So when this happen, see, this one will be the electric field. Okay, if this one is positive and this one is negative, electric field directions. So this electric field, yes, you can choose. Maybe he want to go through from here. Okay, maybe he want to go through from here. Maybe he want to go through from here. But no matter what path he choose, he must pass through two material, right? Two material, two material. No choice. Okay, if you go to here, still two material. Go to here, still two material. Here, still two material. When you have no choice and you have to pass through two materials, then this one is the series. It's the series configurations. Right? Clear? I hope you understand. So for the series, okay, the C total will be equals to C1 plus C2. The total capacitance. Total capacitance. All right, so now let's replace this one. Okay, so for the C total, okay, C1, okay, C1, okay, maybe we'll calculate C1 first. All right, calculate C1 first. So for the C1, okay, we're using this equation, using these equations because the shape is a sphere. It's a sphere. So I will put 1 over A minus 1 over B because this is formula. Formula. So formula says that this is the inner radius, right? Inner radius. And this is the outer radius. Outer radius. Radius. Okay, so we look at C1, C1, 1, 1. Okay, C1 is this one. Epsilon R1. So which is this one? You have the epsilon R1. Okay, so the inner is C. Outer is B. Am I right? You can look at it. C1. Okay, C. This is C, the radius, inner. and this is the outer. So, okay, this one is going to be C, and this one stay still the same B. Still the same B. Okay, so it is 4 pi epsilon naught. Okay, so the epsilon R you can check for the C1 is 2.5. 2.5 over 1 over C. 1 over C. What's the C value? C is 2. B is 3. C is 2. B is 3. 3 millimeter. Okay, so you can calculate the C1. You have to include the milli. Milli. So this is 0.33. Pico. Alright. 0.33. 0.33. So continue to C2. Okay, so we will have 4 pi epsilon. Okay, so for the inner, let's look at the C2. Okay, C2 is here. C2. Inner is A, outer is C. Okay, inner is A, outer is C. It's minus, right? Minus. Or I put again this plus. Plus or minus? Minus. Okay, so this one should be minus. Minus. Okay, so correct back this thing. Minus. Okay, then sorry. This one will be 1.67. Still pick off, alright? Okay, we go back here. So this one will be epsilon naught 3.5. Okay. So 1 over your A is 1 millimeter. 1 millimeter minus the C is 2 millimeter. Okay. So you can calculate the answer. Okay, so you have a 0.78 pico. Alright. Okay, so now is the C total. Okay, is 1 over C1. Sorry. Okay, 1 over C2. Or the other formula. Okay, same. These two things same. So C2, C total is 1.67, 1.67, 0.78, 1.67 plus 0.78. Okay, picofarad. I don't insert the pico. Okay, so it is 0.55 picofarad. Is it correct? 0.5553. Okay, something like that. Okay, now we move on to the second one, B. Okay, B. This is also a spherical capacitors, but if you look at the dielectric material in between the inner and also the outer, okay, they are split in this way. Okay, again, I want you to tell me whether we can still use these equations. Whether we still can use these equations. If you think that you still can use these equations, please raise your hand. Answer is we cannot use that. Okay, why we cannot use? Because the shape, okay, the shape is different already. The shape is different already. Okay, the shape is different. Why I say the shape is different? When you look at the capacitance now, okay, for each of the material, okay, the shape will become like this. Okay, obviously it is not a complete sphere. It's half of it. So this is the equation we derive when it is a complete sphere. Okay, so for this as questions B, we have to rederive. Okay, we have to rederive. So what should we change? Okay, what we should change? So we look back at our spherical capacitors. Okay, this is what we have. Okay, so just now, okay, Q, we have the Q, and this is the Gauss law, right? So when you see the shape is different, it is already half, right? Half. So when the sphere has been cut into half, it means that the angle will be different, right? If it's a complete sphere, it will be 360 degree. But when you cut into half, it will be 180 degree. Huh? Right? 180 degree. So means that there will be some modification over here. Okay. So for the phi, okay, for the phi, let me check the theta. Yeah. For the phi over here, okay, is the rotations, okay, of the sphere. So it is not 2 pi anymore, but it is pi. So this is the things that you have to change. This is the things you have to change. So we will write down here. So you have 0 to pi, 0 to pi. Okay, the d is in the r directions. Okay, dot product with the r square sine theta, d phi d theta. Okay, and r directions. Directions. So this is a dx. The whole thing over here is a dx. I explained before where this thing from. Okay, look at the formula sheet. So this is cancel out, right? Okay, so you have the d r square. Okay, when you integrate the this one, okay, integrate from 0 to pi, this sine theta d theta, okay, you will get 2 pi. You will get 2, sorry, you will get 2. Okay, and the other one you will get pi. Okay, so you can see the difference. Okay, you will get 2, and this one you will get pi. You will get pi. You can press calculator if you don't understand. 0 to pi sine theta d theta. Okay, this one will give you 2, and when you integrate this d phi, this one will give you pi. Okay, so you put it here. So your e, right, 2 pi. So your e will be equals to q over epsilon r square 2 pi. Epsilon. Okay. Yeah, so it is in the r directions. For example, r directions. Okay, so now you compare this one with the previous original one. 4 pi epsilon r square. Okay. Previous one is, where's my pen? Previous one is uh, 4 pi epsilon r square and this one. So this one's still the same, right? Okay. Epsilon you still have, r square you still have. You see this is 2 pi and this is 4 pi. Okay, so 2 pi and 4 pi. So it will be reflected here over. It will be reflected here too. So what's the things that you will change? Any idea about this? What is the things that you will change? What's the things you will change? It will become 2 pi, right? It will become 2 pi epsilon over 1 over a minus 1 over b. Because this thing changed already. Okay, so go through very quickly. We'll go through very quickly. Minus, so this is AB, inner radius, outer radius. Okay, so dr, I will skip, because same thing. I will skip. This is dr. Okay, so you will have this. Okay, so you got the formula. Okay, so the difference is over here. Is 2 pi. So this capacitance, okay, is for the structures when it is in this shape. Okay, when it is in this shape, half of sphere, half of sphere. Okay, so now you combine two. Now imagine, okay, so you have one capacitors, okay, like this, okay, combine with the other capacitor, okay, that has different material, okay. It is one is R2, one is R1, R2, R1, epsilon R2, epsilon R1. So this is epsilon R1, this is epsilon R2. Okay, so again, I want to ask you, okay, what kind of configuration is this when you arrange two capacitors in this way? What kind of configuration is this? If this is the direction of electric field, what kind of configuration is this? Is this series or parallel? Yes, very good, correct. This is parallel. Because the electric field, it has choice. Okay, if he don't want to pass through this epsilon R1, he can go here and pass through the epsilon R2. He has choice. So this one is a parallel capacitance. So for the parallel, the C total will be C1 plus C2. Okay, so now we calculate the C1 using the equation that we have here. Okay, 1 over A minus 1 over B. So here we don't have a C, only A and B, A and B. So it will be 2 pi epsilon for the C1. C1 is 2.5, 3.5. So this is 1 and also 3. 5. So you have 2.5 epsilon naught. Okay. 1 over 1 millimeter minus 1 over 3 millimeter. Right. So you have the 0.21 picofarad. Is it correct? Okay, if you complete this one, you can go to C2. Okay, so I'll straight away use this one is 3.5. So you can just 3.5. So this is 0.29 picofarad. So the C total, okay, will be 0.21 plus 0.29. Okay, so 0.5. It's not 0.5 but 0.5 picofarad. Okay. Okay. All right. Any questions? If no questions, maybe I want you to look at this one. Yeah, let's look at this one. This is actually one of the past year questions. One of the past year questions. So let's try this. Let's try this. Eh, Okay, so now you have a parallel plate capacitors. Okay, you see, with the surface area of 4 meters square. So here you see two lines, right? Okay, shows that the terminal is over here. Okay, terminal is over here, and the surface area will be here. Mouse. Okay, so surface area for the plate is here. The surface area. Okay, and this is the separations. This is the separations. So the plate separation is 4 millimeter. So it contains 3 dielectric material. Okay, something like this, and it looks like they are the D for each material is the same. It seems like the same. They didn't mention. Find the total capacitance of this capacitor. What's the total capacitance? What's the total capacitance? Right. So first of all, you have to decide, okay, whether this is series or parallel capacitance. Okay. So this is the plate, right? Plate. So this one will be positively charged, for example, and this one will be negatively charged. So electric field go through in this way. Right. So this is a series capacitor. Series capacitors. So you have series capacitor. Okay. So you are going to find series capacitance. Okay. So what is the series? First formula for the series. C1 plus C2 plus C3. right? Okay, series. So what is C1? And what is C1? C1 equals to epsilon x over D1. This one. Okay, let's put it this way. I will put it this way. So epsilon 1 is 3. 3, right? So the surface area same, okay? Because for each material, it occupied the whole plate which has a surface area of 4. 4. And the separation over here, I guess they are the same because they didn't mention, so we just assume they are the same. Okay, so it will be d divided 3. D divided 3, which is 4 divided 3. 4 divided 3. So you can calculate this, right? Calculate this. So it is 79.7 picofarad. Okay, so for C2, you can using the same technique. So you have 3, 2.5, and 7. So you can calculate it. 0.5. Okay, 7. Okay, so I group it into picofarad lah. Okay, easier for you to calculate. So now you can calculate this CT. So I take out the pico when I do these calculations. Okay, and the one you get is 1 over CT. Okay, 1 over CT. Come so high. Oh, pico. Okay, okay, okay. So this is 0.03. Okay, 0.033, and this CT is equal to 30 point. Is it correct? Nano. Oh, 4 milli. Okay, I'm sorry. Here should be 4 milli. 4 milli. Okay, 4 milli. Right. So this one will be divide milli. Yeah, so it should be nano lah. Should be nano. Should be nano. 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 So this one also nano. Okay, this one should be milli, 4 millimeter divide 3. Okay, so this one is nano. 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 Okay, alright, we move to the second one. So if the middle dielectric material is replaced with a new material, okay, so this new material, it has its own dielectric constant. Okay, we don't know what's the value. So they ask us to predict, okay, so calculate back, okay, what is the dielectric constant so that the total capacitance, okay, is 39.28. 39.28. So just now we have this one. So now they are going to change this second material. Okay, second material, right? 2.5. Okay, they are going to change it. Yeah, this 2.5, they are going to change it. So that this one, they will get 39 point something nanofarad. Okay, so like you have to calculate back. Okay, what happened? Okay, if this one is 39.28, 39.28 nanofarad. So how about this? What will happen to this value? So you can calculate back, right? Okay, so it will be 1 over 39.28. So you will have a 0.0254, something like that for this one, if you calculate back. So this one fixed, this one fixed, this one is a variable. This one is a variable, so you have to calculate back. Okay, so you write down 1 over 79.7 plus 1 over x, okay, x something you don't know, okay, plus 1 over 185.9 will give you this 0.0254, right? This one will change, okay? So what will be your 1 over x? Okay, so you have to find out by minus 1 over and minus 1 over 79.9. So this one will give you 7.53 milli. 7.53 milli. So this thing, you move it to the right. Move it to the right. So meaning this one minus this one and minus this one, you get this. Okay? And your x, of course, you can get it. Okay? It is 132.77. And this one supposed to be the value of the capacitance. So it will be nanofarad. So this one will be the C2. Maybe I'll put C2 easier. C2. 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 Okay, so what can cause the C2 to be this value? So all you have to reverse back. What is C2? C2 is this one, right? C2. So C2, okay, is equal to epsilon R naught. So just now we have the surface area, which is 4, and then 4 millimeter over 3. This one is the distance, right? Okay. So now you have your C2 is 132.77 nano. All right. So this is something you don't know. So you know epsilon naught. Okay. So you can find it back. You can find this thing back. So this one will be, okay, you can press calculator. So here you have to include a nano. You have to include a nano. So get 4.998, something like that lah. Or you can approximate it to 5 lah. So who has problem to get this epsilon r? I don't show the steps. You can straight away press calculator to get this thing. But I wish to know who cannot get this 5. Who don't know how to use your calculator to get this 5. Can you raise your hand? Okay. So for this one, okay, how to get this thing? Okay. So first you move this thing over here, right? You have to move this thing. So it will be 137.77 nano. Okay, you multiply with 4 millimeter over 3. Okay, now you want this thing. So this one you have to divide here. Okay, and divide epsilon naught 4. Okay,
So doktor, yang kita nak darab tu memang dalam kurungan kan macam biasa?
which part? Which one? Mana satu?
Yang yes, the 4
Ini.
ya,
Ini.
dalam kurungan kan? Yes.
Yes. Tak semestinya dalam kurungan. You boleh buat this one first. Actually, this one it will go down lah jika by the mathematical formula. Okay, so dalam calculator you boleh tekan ini darab 4 mili bahagi 3. Tak semestinya ada kurungan sebab ini ialah darab, dia bukan tambah. Jika tambah kena ada kurungan. Okay, jika darab tak perlu. Okay, ini darab ini bahagi ini dapat jawapan bahagi lagi 4 epsilon naught.
Thank you doktor.
Okay. Okay, so you get this 5. You get this 5. Okay, so I'll proceed to the last one. Last one, which is this one. So if an engineer wants to increase the capacitance, what suggestion you could give to him or her? Okay, any idea how to increase the capacitance? Any idea? How to increase the capacitance? Okay, you can see this capacitance formula. Right, S over D. So you can increase the capacitance by increase the area, right? You can increase the area of the plate, right? Area, and you can reduce the plate separations. Plate separations. And if you based on the calculations of question 1 and 2, you can see this one is lower, this one is higher. Okay, so what happens is if you increase the dielectric constant of the material, okay, it can actually increase the capacitance, right? So as this one also show already, you increase the dielectric constants of the material, then you will be able to increase the capacitance. So this one is nothing to do with the calculations. So it's based on your understanding. So your understanding can be assisted by your formula. Based on formula or based on you see this is the calculation that you have done. Okay, you see what happened when you replace this one. Okay, initially 2.5, you get 30.32. Okay, when it is 5, you get 39.28. Right, so you expect this one also the same. If you increase this one to 10, okay, of course this one will increase as well. Okay, if you reduce it, okay, this one will reduce. You can say from here also. Okay, you can say from here also. So you can type your answer here. Okay, so the capacitance can be increased by increase the surface area of the plates or the dielectric constants of the material. Okay, besides that, okay, reducing the plate separations separations can reduce, sorry, can increase the capacitance as well. So your answer should be in centers. You explain about what you understand. Okay? Okay, so I think that's all for today's tutorial. So if you have further questions, you can stay. Right. So in this week we have learned, okay, just go through one more time again. Okay, we have learned the how to derive the capacitance. So these are the steps that you can use to derive the capacitance. Okay, so whether you need to re-derive the capacitance or not, it depends on whether you change the shape. Okay, if you change the shape of the cylinder, if you change the shape of the sphere, then you need to redrive. Okay, if you don't change the shape, you can just use it. Okay, but the thing is, you have to identify, okay, whether it is parallel configurations or series configurations. Okay, I guess all of you will know, because just now when you, based on what I see, how you raise your hand, I think most of you will know. I don't know what happened for those who don't want the response, whether you are not around or you don't know. Okay, please try to make yourself clear about this. Okay, right. So I think that's all for today. Thank you very much.